Great.
Thank you very much.
I'm gone.
Thank you, Karen, for inviting me to come and speak today. I suppose I'm slightly different from some of the other presenters because I run a business that's involved in the area of underwater wireless communications and control. So the company's called WFS Technologies, and we build primarily radio-based underwater wireless communication systems. So I'll tell you a little bit about the company, the underlying technology we work with, which we brand name Seatooth, and a little about the applications where we will work on in the oil and gas industry, which is the bulk of our activity, and a small amount of work in the defence industry. And from our perspective, where we see the world is going. So this company was started around about 12, 13 years ago in Edinburgh. So we're both come from the hairy north down to what's much too warm a room for me today. Company's privately owned. We initially worked in quite a different field from underwater radio. Our initial applications were actually in the early forms of Wi-Fi and ground-to-air communications to support communications with unmanned air vehicles. And a little bit by accident, we became involved in underwater vehicles. And as an internal experiment, we decided to play with low-frequency radio just to see out of interest if it would work. And to our surprise, we could build pretty basic two-way communication systems that operated over 10 metres plus underwater. What I'd loosely call conceptually Bluetooth-type functionality in an underwater environment. Thought this was a neat idea, couldn't find out any other companies selling equivalent products, so we flipped the company and became an underwater radio communications company. And really, since the start of our work in that area, when it was about 2004, we've invested over 200 man-years in the development of this underlying technology. Now, radio communications is quite unusual from an underwater perspective because it actually predated air-based communications. The world's first recorded EM propagation was actually underwater, and it was by accident. It was by an American called Morse. He ran a telegraph wire across Hudson Bay, and it broke. And he noticed there was a pulse, an impulse transferred across that cable. An interesting observation, almost what I call a penicillin moment, but he looked at it and thought, neat idea, but he was off in the telegraph race and he got on with doing other activities. But substantial further work was actually carried out in underwater radio, of all places, in Dundee in Scotland in the 1850s, where a professor tried to build a transatlantic communication system and did not succeed, but he built some quite neat underwater electromagnetic-based pulsing systems. Then the technology was largely forgotten until the First World War, where low-frequency radio was used as a communications technique in the trenches. And then after that, it was used in the Cold War to develop ELF systems for submarines, broadly around 70 to 82 hertz. And systems were developed in the US, UK, France, and Russia to support very low-frequency communications. A substantial body of research was really carried out in this area broadly from the 1950s until the end of the 60s. It dropped like a stone. There were almost no further papers in this field right through the 70s until the mid-80s, when there was a small blip in Heriot-Watt by chance, where Professor Heriot-Watt carried out a few years of work in low-frequency radio, and then it died again until we picked it up again in the around about 2004. So it's a curious field. It's actually been around for a very long time, but until relatively recently it hasn't had its moment. So part of the reason people kept dropping the technology was the intended purpose of communications underwater was long-range communications across the Atlantic, and the technology is no good for that. It's fundamentally a short-range communications technology that is broadly equivalent to Bluetooth or Wi-Fi and ultimate functionality. So we've carried out a substantial body of work, gone right back to first principles, worked on Maxwell's equations, developed the underpinning phenomenology, developed modelling tools, developed our own modelling tools to cross-correlate the theory with practice, built experimental systems. We've carried out low TRL work with the MOD in the UK and DOD in the US to try and understand the underlying space around what's the envelope of the possible of low-frequency radio communications in this domain. And then really over the last 5 to 6 years have we taken that underpinning research and moved it across into products. And today we sell off-the-shelf COTS, in military terms, radio products for a range of applications. And the bulk of our work is in the oil and gas industry. We embed our products, a bit like a little Wi-Fi card, into subsea instrumentation and treat it as a Wi-Fi enabled pressure transmitter or temperature transmitter or flow meter, etc. So our technology is ultimately lost within the functionality of another product. But there are a number of interesting applications of the technology in the defence industry as well. And really over the last 12 to 18 months, WFS has revisited defence applications of the industry using off-the-shelf commercial products that we've developed. So here's an example of a picture of a Wi-Fi type network that's deployed on a platform in the North Sea. The particular platform is called North Cormorant. It's around about 200 metres of water. And on this platform we deployed a dozen underwater wireless nodes, each spaced around about 30 metres apart, and they were deployed to carry out long-term asset integrity monitoring. So each one of these nodes, the underwater nodes, are configured to take a corrosion reading of the rig at 6 different levels along the rig every 12 hours, and then wirelessly stream that data straight through the water air boundary once a week. So at the end of the year, the operator has around about 1,000 data points as an alternative to them sending a diver or an ROV once a year to get a single data point. So we're offering 3 orders of magnitude more data, and the installed cost of this system is less than the cost of sending one diver out to take a single data point. So that's really where we're transforming the oil and gas underwater world. So a little bit about the underlying technology we work with. The bulk of our work is in low-frequency radio, but we also build inductive power transfer systems. That's really been driven around applications around AUVs. We see a long-term need to provide wireless docking, data plus power docking for AUVs, for the subset of AUVs that we see will ultimately be deployed permanently at the seabed. That's an area that has not yet arrived, but we see that coming through over the next 5 to 10 years. In terms of the what's possible to achieve with the technology, well, many of our devices communicate at around about 100 bits per second, which superficially is a very low bandwidth, but for process control systems, we are transmitting pretty basic temperature data or corrosion data that's perfectly fit for purpose. On these devices, we can communicate through around about 40 odd metres of seawater, or a couple of hundred metres of air, or if we take the same nodes and place them on the seabed, the propagation path through the seabed is much more effective than through seawater. There is ultimately a lower conductivity in the seabed, and the propagation range node to node of these systems extends out to in the order of 200, 250 metres. And we can set these up as wireless networks across the seabed. The devices we use most commonly, this yellow device up top, that's a device that supports a couple of kilobits per second at anywhere between 7 and 15 metres through water. That yellow can is a 4,000 metre depth rated enclosure. We've deployed these systems in deep water in the Gulf of Mexico. We've got some of these deployed at a couple of thousand metres in just off Japan in 80 degrees centigrade water for some quite interesting applications. But we can also take the technology and stream video at around about 100 kilobits per second, and we rent Wi-Fi enabled underwater cameras for a range of asset integrity monitoring applications. We can also take Bluetooth type Wi-Fi type devices, integrate them into underwater enclosures and turn them into wireless connectors where we can communicate between 10 and 100 megabits per second at around about a centimetre. So it's basically replacing wet mating connectors. And then finally, we've got a variant of our product that operates at very low frequency, sub-100 hertz, which we use to communicate through steel. So we can communicate through pipe-in-pipe, which is a commonly used process in the North Sea for transferring hotter liquids. And the purpose of communicating through pipe-in-pipe is to provide two-way data communications with pigs and pipes to locate the pigs, but also to turn it the other way around to treat the pig like an AUV on tram tracks to allow the pig to harvest data from sensors on the outside of the pipe. So it's another method of harvesting data. So we build power transfer systems up to around about 3 kilowatts. And we go one step further with our sensors, and we've developed a number of solutions around the oil industry built around fatigue management and corrosion management. So a couple of the devices here, that's a sort of standard off-the-shelf wireless data plus power connector. This is a wireless communication system with a rebreathe system that's part of a safety system we've developed with a company called Danavex. And this is a risk controller on a motorised surfboard. For those of you who get to my age, somewhat above 40, get a bit lazy and you don't want to swim out to the waves in your surfboard, you can buy a motorised surfboard from a company called Wavejet. It's a bit like a Segway on water. And the reason for having a wireless disconnect on the device is if you fall off the surfboard, you don't want it disappearing off into the distance a couple of kilometres. It acts as a wireless disconnect on that device. So that's a truly commercial product. We sold quite a few thousand of those devices. So I perceived this was going to be a deep technical conference, so I put in some graphs and charts. So I understand there probably aren't that many physicists in the room. But this gives you a little bit of a flavour of some of the background work that's been carried out in this area. So fundamentally, electromagnetic propagation in seawater is challenging. It's very, very tough, and that's really why it hasn't been carried out that often. The attenuation is pretty aggressive. It's in the order of 55 dB per lambda, about 55 decibels per wavelength. And to flip that round the other way, the maximum practical range through seawater is in the order of 2 lambda. So the range is to an extent a function of the carrier frequency of the system in water. One of the other interesting attributes of electromagnetics in water is the propagation velocity of EM is significantly higher than an acoustic equivalent. It's not the speed of light in water, other than if you're at light frequencies. In fact, it's interesting, if you drive the carrier frequency of EM right down to around about 1 hertz, it's around about the same velocity of acoustic, which is very roughly 1500 meters per second or thereabouts. But most of the carrier frequencies we work with, which are typically in the small numbers of kilohertz up to megahertz, the propagation velocity is many orders of magnitude faster than acoustic. So that leads to low latency within systems where from time to time that's relevant. So a neat attribute of electromagnetics is we can communicate straight through the water-air boundary, two-way through the water-air boundary, and through the seabed boundary we can communicate through concrete blankets in the seabed to sensors that are buried. We've run systems where we've communicated through several meters of ice. So we can go through a number of barriers. And when we started this process, we weren't really quite sure what were the physics associated with propagating EM signals through such barriers. And we invested quite an amount of resource in developing modelling tools to help us to determine and predict the performance of systems. But the real bottom line is, for most of the systems we build, the propagation loss through the water-air boundary is relatively low and really quite manageable. So what range is possible using electromagnetic systems? Well, that answer is actually a bit complicated. It sort of depends what you're trying to achieve. So if you start with the premise of I'm trying to propagate through a perfect sphere of seawater with a constant constant attenuation factor, we have built systems that will communicate through 30, 40 meters of seawater at 100 bits per second. Those are commercial products that sit in this band, or 100 kilobits per second through in the order of 5 meters of seawater. So we've built devices that sit roughly in this band, and we have also devices that communicate through short ranges at very high bandwidths. But, as I mentioned earlier, if you place a radio device and put it onto the seabed, the range extends. In fact, this graphic at the right shows pretty much what happens, particularly in shallow waters. It's not always that easy to predict exactly what the final propagation path of an AM system is in shallow waters. It will typically seek to propagate through the seabed or the air boundary if it can. It ultimately finds the path of least resistance. But it can be quite complicated to predict what the final performance will be. So to give you an idea of sort of quantums, we built a demonstrator system a few years ago for locating target application, locating an AUV lost under ice. And the trials we carried out, we communicated through 5 meters of seawater plus around about 750 meters of air at around about 10 bits per second, which was a perfectly competent sort of range performance for a location system. But still, within the context, not a transatlantic communication system for submarines, and far, far from it. So that's a little bit about radio. But big picture, radio is no better than acoustic and it's no better than optical. None of these technologies is better than the other. They simply have different attributes. Each one has pros and cons. And we are ardent advocates of hybrid systems, bringing multiple technologies together in exactly the same way that Takara mentioned fusion. We think fusing different communications technology is the only route to the future. So, for example, radio systems are particularly effective in challenged environments, in littoral waters, Radio is unaffected by turbidity, by bubbles, by sea life. It can work seamlessly through the water-air boundary. Very, very challenging environments. In fact, environments that are virtually impossible for acoustic systems to operate. Flip side is, radio systems will never achieve 1 kilometre or 2 kilometres through clear blue sea water. That's just not on the map. Optical systems are interesting because fundamentally they can deliver extraordinarily high bandwidth, but they're also quite limited in the way they operate. They need a good clear line of sight. They're also relatively susceptible to turbidity in the water. So what are we doing with this technology in the oil and gas industry? Well, the bulk of what we're doing is actually very, very basic first level, what the US would call 101 level automation. The oil and gas industry, subsea oil and gas industry, is surprisingly almost antediluvian in its approach to industrial controls. So one of our advisory board is BP's former chief engineer, and openly admits that the oil and gas industry operates what he calls agricultural technology. It's what he describes as the Harley Davidson of the motorbike world. Big, clunky, thick pieces of steel that they haven't really modelled, and contrast that with the Japanese bikes that scream down a road that are brilliantly engineered. And one of the challenges of the oil industry is so much of the underlying industry is built around predictive models in corrosion and in fatigue and flow. And these predictive models are very rarely cross-calibrated against real-life measurements and instrumentation. So, for example, in the design and build of what's called a riser is a large oil or gas pipe that rises from the seabed to the surface. In the design of a riser, the fatigue model that's used for designing those is typically oversized by a factor of 10 to 20. So, to turn this round another way, it's only used 5% of its life before they throw it in the bin. And ultimately, that is extraordinarily expensive. Cite another example, I haven't put it up on one of these slides. We built a real-time fatigue monitoring system for a Brazilian company called Petrobras and a US service company called Halliburton last year, where they were using a type of steel pipe called coil tubing. Coil tubing is a bit like a reeled hose pipe made out of steel that goes in very, very large reels. These large reels sit in a boat that costs about $1 million a day. And they reel this into the water. And if you've got this very large boat with a hose pipe sitting below, and the boat is exposed to bobbing of waves, and that bobbing of waves introduces fatigue. It's called elastic fatigue. Now, historically, or hitherto, it hasn't been possible to measure the elastic fatigue in the tubing. So the supplier of the service has typically put in a broad brush 5 times safety factor on the coil tubing. So that 5 times safety factor means they throw it in the bin when it's 20% used, because they don't know what's going to be used. What we've done for them is taken our off-the-shelf technology, built a simple wireless network of sensors comprising strain sensors and accelerometers, developed some software to convert that data into real-time stress, strain, and elastic fatigue, and give the operator the equivalent of a fuel gauge that tells them, this is how much fatigue life you've used up, 20, 30, 40, 50%. We don't tell them when to take the tube out of action. It's their call on when they do it. So it's their call if they were on a 5 times safety factor, or 4 times safety factor, or a 3 times safety factor. But the analogy is, too many moons ago when I was a student, I had a really dodgy old car and the fuel gauge very rarely worked. And it's quite interesting driving a car without a fuel gauge. You can, and many of you probably have, but your behaviour changes. Behaviour changes radically. So depending how conservative you are, you might fill up at every single petrol station you drive by. Or other people might say, can I take this right into the red? Can I do that? Maybe occasionally run out, but it's very much down to personality. So if you move into very conservative industries such as the oil and gas, if you don't give people instrumentation equivalent of a fuel gauge, they run extraordinarily conservatively, this factor of 10 or 20 safety. So the bulk of our work right now is actually working with the companies that deliver the most widely used predictive models in the industry, fatigue models, corrosion models, flow models, to match up our instrumentation, long-term deployed instrumentation, to help them to correct those models, to reduce what I call the slack in the system, and ultimately to drive down the costs and to drive up the safety. So that's effectively our day job in the bulk of the industry. And this is a typical example of the sort of system that we deploy, is putting a sensor or multiple sensors on an asset underwater to allow that data to collect 1,000 or 10,000 data points a year to start to build a much better picture of what's going on to cross-calibrate. So defence, so where can we use this technology in the defence? So if I go back 5, 6, 7 years, we were fundamentally a contract R&D house and doing some pretty interesting low-tier research for defence, but we didn't think that was our future. We wanted to move into products. But now that we have products, interestingly, we are seeing quite interesting opportunities to take those same off-the-shelf products, which are pretty low cost compared with most defence systems, and provide them back into the defence markets. So if I look at the underlying attributes of C-tooth technology, where can it be used in this industry? Well, we can stream data, voice and video systems, and we do so on a pretty regular basis. We can stream data through water, through the water-air boundary, video likewise, through short ranges, through water, through the water-air boundary. We've even, although we don't have a commercial product, we even demonstrated voice communications through the water-air boundary. The technology is extremely resilient. It's actually more resilient than any other wireless technology currently available in the defence industry to those environments that are most challenging, particularly littoral waters. The technology is not a long-range technology, and it's never going to be a long-range technology. The flip side for this industry, for the defence industry, is that has a positive attribute, and that's relatively covert. We can define the maximum distance that's possible for anyone to pick up radio communications underwater. And it's pretty straightforward to lock and key a system, so it's completely secure on either end. And it's extraordinarily energy efficient. So we've developed some underpinning technology that allows our radios to remain in an always-on condition for between 10 and 20 years on very modest battery packs. That underpins much of our work in the oil and gas industry. So we see prospects in not just the oil and gas industry, but the environmental industry and defence industry deploying sensor networks across the seabed carrying a range of sensors, and it's down to the customer to determine what those sensors are, picking up data and processing that data locally. So we've a variant on your theme of marine Internet of Things. We happen to call it subsea Internet of Things. Great minds think alike. Right at the core of our architecture is to do as much data processing as you possibly can at the centre and only retransmit information. And part of the argument for that is the necessity. The most expensive thing for us is battery power. And battery power is used by transmitting data. So the less you transmit, the longer the life of your system. And at the end of the day, excuse me, in the oil industry, if an operator receives a terabyte of data on his desk, what does he do with it? He sits for 6 months and frankly does not an awful lot with it until someone else does something with it. So why not process it at the seabed into something useful? Because frankly we can put a little target computer down there to process that data using the same algorithms that he would use on his desktop. That's exactly what we're doing. And then retransmit that data either by networks back to shore through the water-air boundary, or to a flyby AUV, or to flyby ROV, or to nearby buoy, or whatever else is appropriate. Excuse me. So what are the other applications of radio technology in this industry? Excuse me. Quite a lot of what we're working on at the moment in defence is actually around safety. It's taking small devices that we've developed for surfboards and turning them into short-range wireless personal area networks to attach body-worn sensors so we can monitor the rebreather or the core body temperature or the breathing of a diver, collect that data, collect it around a black box, available either as a standalone device or to communicate it to a buddy diver so that each person knows the condition of each other. And then, as appropriate, transmit that data back to surface if there's a particular problem. We see some very significant opportunities around using this technology in these short ranges, really in safety in this industry. But we also see some interesting applications in the technology to support divers' communications with sort of delivery vehicles and with AUVs. So if you're in the land-based soldier, will typically today in a hostile environment work with autonomous vehicles. Either very small eyeball-sized robotic vehicles that they will throw over a wall to act as a set of eyes to see what's going on. The underwater world doesn't yet do that. In fact, the first place that we've seen that started to do that is a research centre in Panama City that started to integrate our technology with ROVs to start to provide much more information to the diver. But the defence industry is surprisingly stovepiped, so the AUV programmes are completely separate from the diver programmes, which strike me as really quite curious. But we think it is almost certain that over the next 5 to 10 years, we'll start to bring those two together. And when we bring those two together, our technology as in radio-based technology becomes really quite a key enabler for two-way communication between diver and AUV, particularly operating in shallow water, because that's really where the diver operates. We've also been developing XYZ location systems using radio systems underwater to allow the relative location of one diver versus another, or a diver versus a vessel, or a diver versus another device to support safety so that people can identify buddy-to-buddy locations. So where do we see the world going? Well, I mentioned at the start, we're really strong advocates of hybrid, and we've got our own hybrid, C2 hybrid program ongoing at the moment, where we're bringing together our own radio technology with acoustic technology. We've partnered with a company called Hyland, and an optical technology. We partnered with a San Diego-based company that produces Li-Fi systems. And we see the future of underwater wireless communications pretty much the same as a smartphone, which will work with, a smartphone today works with half a dozen radios, and they're clever enough that we don't particularly know which radio they're using at any point in time, whether it's 3G, 4G, Bluetooth, Wi-Fi, NFC, whatever happens to be on it. And from a user perspective, it just does what it needs to get on with. Our view is the future of underwater communications is exactly the same, that a system will seamlessly move from the radio to the acoustic to the optical domain to provide the most cost-effective, in terms of battery power, or the most reliable communications, or if it's appropriate, the most covert communications for a particular operational environment. The second area that we're particularly excited by is what we call reachback, is to allow conventional above-water wireless communication systems to directly link and provide persistent communications with divers, with AUVs, with SDVs, in environments where today it is just not possible to do that in relatively shallow water. We think this could be a game changer for many people in these challenged environments. So where do we see the technology going in terms of performance? Well, nodes placed at the seabed. Today we can achieve in the order of 250 metres between nodes. We're quite confident we can push that out to about 1 kilometre. We think the science might allow us to push further, so we've yet to visit that. But building persistent sensor nodes spaced up to 1 kilometre apart, long networks spanning out in from shore out into several miles into littoral waters to support sensor networks for environmental monitoring, for shipping channel monitoring. We could even use them as the equivalent of landing beacons to provide navigation for vehicles, whether it's above water vehicles or underwater vehicles or divers. And we see battery technology pushing out yet farther. So we do not invest in the development of battery technology. We use off-the-shelf, high-quality industrial batteries. And the battery technology that we use is really being driven by the electricity utility meter market, where the requirement 5 years ago was for batteries to last 15 years. That's pushing out to 20 years today, and very shortly will be 25 years. We're using exactly that technology. So in summary, our perspective is the subsea Internet of Things is coming and coming fast, and really it's coming on the back of the Internet of Things, which is being driven out, particularly in an industrial basis. We see hybrid technology becoming the norm over the next 5 to 10 years, and smart systems being a component of that to much, much more intelligent things at the remote sensor. We see radio technology being a core component of those future wireless networks underwater. The wireless technology today is much more mature than most people perceive. It's a truly persistent network, given it can operate in so many adverse environments, and it's highly secure. And we see significant opportunities to use COTS technology in a range of the most challenging littoral water environments. Thank you for your time.